Today you are going to learn what derivatives are as if there were no tomorrow. It's essential that you understand all the information I'm going to share in this video, because it's the foundation, the building blocks for what's coming in the next videos. If you grasp everything I explain, your adventure with derivatives will be an amazing journey. So stick with me until the end, and I promise I won't let you down. Welcome to Binnacle Project.
Binnacle Project.
Let's start by clarifying the first concept. What is the derivative at a point? Look, here's a function, just like the ones you've seen before. You probably already know how to find certain features of it, like the x-intercepts, the y-intercept, and so on. Well, today it's time to learn a very important property of any function, its growth. To understand the concept of a derivative, I want you to imagine that we are traveling along this function from left to right. We always go left to right, as if we were riding a roller coaster. This little ant named Hypatia is going to help us. Here we have Hypatia on a section where the function is increasing. Now she has just reached a maximum, where the function is neither increasing nor decreasing. It's perfectly horizontal. And then she starts a section of decreasing. Now she's at a minimum, again neither increasing nor decreasing. We see how she starts increasing again and reaches a point where she's perfectly horizontal before continuing to increase. A point like this is called a point of inflection with a horizontal tangent. Then she continues to increase. But we don't just want to know the increasing and decreasing intervals. We also want to know how much it is increasing or decreasing. Because, as you can see, here Hypatia is increasing less steeply than she is here. And here, she is decreasing less steeply than she is here. In mathematics, qualitative answers aren't enough. We need quantitative answers. And that's where derivatives come into play. To get there, let me take you back a few years ago. Let's go. Here's a straight line with a slope of 1. Do you remember? The slope of a straight line is the coefficient in front of x in its equation. This other ant, let's call her Gauss, is walking along with a slope of 1. Can you tell me the slope of this other line? Go ahead, it's easy. As you can see, to move between 2 points on the grid, we move 2 horizontally and go up 1 vertically. Its slope is 1/2. This other ant, let's call her Nether, has a slope of 1/2. We could keep creating an infinite number of lines with increasingly steep slopes. This ant is walking on a line with a slope of 2, because we move 1 horizontally and go up 2. Let's call her Sophie. And this is a line with a slope of 3. We move 1 horizontally and go up 3 vertically. Let's name this ant Leibniz. The greater the slope, the steeper the line. Now, let me remind you what a line with a slope of 0 looks like. Here it is, horizontal lines. As we move forward, we don't go up or down at all. Take note of this situation because it's super important for this topic. Ants on lines with a slope of 0 are perfectly horizontal. Let's say this ant's name is Tails. But we can also create lines with negative slopes. Here's a line with a slope of -1/2. We move 2 horizontally and go down 1. Let's call this ant Ada. This other one has a slope of -1. We move 1 horizontally and go down 1. You will be Pythagoras. And so on. The more negative the slope, the steeper the line inclines downward. This ant on a slope of -2 will be Emily. Now comes magic. Stick with me because we are almost there. Let's return to our function. Remember, we were trying to figure out a quantitative way to measure how much Hypatia is increasing at any point in her journey. Let's stop Hypatia at this point, where the x-coordinate is -6. Doesn't it look like she has the same slope as Sophie? We can say that Hypatia's slope at x equals -6 is 2. Now Hypatia is completely horizontal, she's at a maximum. Her slope at x equals -5 is like tails, 0. Now Hypatia has the same slope as Ada. Her slope at x equals -4.5 is -1/2. Let's keep going because you are getting the hang of derivatives. Now Hypatia has a slope like Pythagoras. Her slope at x equals -4 is -1, and so on. As you can see, a wonderful way to measure how much an ant is growing at a point is the slope of the line passing through its feet, and this is the derivative. If someone ever asks you for the definition of the derivative at a point, please don't talk about ants or feet, because they might think you've lost your mind. Instead, say this. The derivative of a function at a point is the slope of the tangent line to the function at that point. Before erasing this image, let me highlight something very important. Look at the ants that are horizontal, like tails. They are always at key points, like maximums, minimums, and horizontal inflection points. These points are essential because they allow us to graph the function and gather precise information. Don't forget, at maximums, minimums, and horizontal inflection points, the derivative equals 0.
Binnacle Project.
Now that we have an idea of how to measure the growth of a function at any point we want, it would be great to have a machine where we could input the value of x whose slope we want to know, and the machine would tell us. Well, fortunately, that machine exists. It's called the derivative function, or simply the derivative. Look. Here we have this function that we can graph. Now, I want you to trust me, because I promise that its derivative function, or simply its derivative, is this other function denoted as f prime. From the function f, give me a value of x whose slope you want to know. For example, x equals -1? Well, if we ask the derivative what its value is at x equals -1, it answers -7.5. The slope of our function at x equals -1 is -7.5. And now that you've recalled the concept of slope, you can imagine that our ant is decreasing, and quite steeply. Here is another example. Let's ask the derivative what the slope of Hypatia the ant is at x equals 0.5. All we have to do is substitute x equals 0.5 into the derivative, and it tells us 1.6. This result is positive, meaning our ant is increasing, and it doesn't seem like a particularly steep climb. But now something even better. What do you think about asking the derivative where ants have a slope of 1? Be careful here, because in this case, we are not substituting x by 1, but instead setting the derivative equal to 1. Then, by solving the equation, math tells us at x equals -0.16, x equals 0.5, and x equals 1.45, there are ants with a slope of 1. See how powerful the derivative function is? And finally, now that you know what this is all about, and remembering that maximums and minimums are very important points for any function, what do you think about asking the derivative where there are horizontal ends. This way, we will be calculating precisely the maximums and minimums of our function. Let's get to it. We set the derivative equal to 0, and math answers at x equals negative 0.25, x equals 0.75, and x equals 1.4. There are horizontal ends, that is, these are the x-coordinates of the maximums and minimums of this function. Determining whether they are maximums or minimums is something we'll see later, but at least we now have a very important tool, the derivative, which allows us to know everything we want about the growth of a function. Now, stick with me until the end, because in 2 minutes I'll explain how to calculate the derivative function and we'll be done.
Binnacle project.
There are 2 ways to find the derivative. One is the quick method, using the famous table of derivatives. This is like a recipe book where you simply look up the function you want to differentiate and you'll find its derivative immediately. This is the method we use when working on math problems because it's fast and simple. And we'll practice it together in the next video. But since this is math and not religion, I'm afraid that on any derivative exam, you'll be asked to calculate the derivative function not using the table, but by definition. This is a longer process and can feel tedious, but you'll need to practice it just in case it shows up. We'll cover it in the 3rd video, and I promise it's deeply satisfying when you calculate a derivative using the definition and discover that it matches the result you get from using the table. So, hang in there. In this video, you've learned about the concept of the derivative at a point and the concept of the derivative function. We've also started learning how to work with derivatives. From here, we'll keep moving forward so that, before long, you'll feel like you've mastered this fascinating mathematical ocean called derivatives. And of course, don't forget to subscribe, give this video a like, turn on notifications, and leave a comment, because it will be a pleasure to answer your questions. See you soon!